If you look closely at this water, you'll notice it is almost impossibly transparent. It maintains a highly stable temperature year-round and has a distinctly alkaline pH. This is a chalk stream. Out of the millions of river systems on Earth, there are only about 250 of these streams in existence. And as this map shows, they aren't spread evenly across the globe. Almost all of them are clustered in a tight geographic footprint across southern England. Zooming in on the foot of the Berkshire Downs, we find the village of Blewbury. The entire settlement is built around a network of these rare springs, which are fed directly by a massive underground aquifer. Because England holds a near-total geographic monopoly on this specific geology, local conservation carries unusual weight. Protecting a single village pond here is an act of preserving a globally rare ecosystem. But if you visit a specific blueberry pond known as the Cleve today, you won't see crystal-clear alkaline water. You will find thick, muddy silt, stagnant flow, and very little aquatic life. To understand why, we have to look back at how this water was historically used. For decades, the natural channels of the Cleve were heavily engineered and straightened to support commercial watercress farming. That heavy engineering left behind a rigid, artificial structure. The stream lost its natural curves and varied depths, stripping it of the physical mechanics required to regulate its own water speed or naturally flush out gathering sediment. The Cleve's current state is an artificial decay, a lingering agricultural hangover that requires deliberate human intervention to resolve. The first major problem holding the pond back is actually growing right above it. Without regular maintenance over the years, large mature trees have formed an unnaturally dense canopy that completely blocks out the sky. That thick canopy sheds massive amounts of leaf debris directly into the water. Because the historical farming channels removed the stream's natural faster currents, those leaves don't wash away. They just sink. Over time, rotting organic matter breaks down into a thick layer of dark silt. It settles heavily over the stream bed, burying the natural gravel. Between the heavy shade blocking the sunlight from above and the silt smothering the gravel below, aquatic plants cannot photosynthesize. Without those plants and clean stones, the invertebrates that form the base of the local food web simply suffocate. The straight agricultural channels slowed the water down, and the overgrown trees filled it with debris. Together, they created a physical trap that the ecosystem cannot escape on its own. Reversing this decline falls to local community groups, but before they can touch the water, they have to navigate a bureaucratic maze, securing strict legal permissions from the various riparian landowners who control the riverbanks. Once permitted, the first physical step is surprisingly aggressive, cutting down large, mature trees. By removing sections of the canopy, they drastically increase the sunlight hitting the water surface, which kickstarts plant growth. The next step is creating what hydrologists call flow diversity. To do this, volunteers take the very wood they just cut down and intentionally place it straight into the stream channel. Placing large logs into a slow stream forces the water into a tight bottleneck. That increased pressure accelerates the flow right underneath the wood, acting like a natural power washer that scours the accumulated silt away and exposes the clean gravel below. Chopping down trees and throwing logs into the water looks messy, but these are precise biological levers required to force an engineered landscape to behave like a wild stream again. Local channel restoration is the first of 3 requirements within the trinity of ecological health, a framework that necessitates the simultaneous management of water resources, water quality, and physical habitat. If a regional utility pumps too much volume from the ground miles away, the stream runs dry regardless of how clean the local gravel is. The local habitat work fails entirely if the overarching water resources are depleted before they reach the village. Scientists propose a massive policy shift: relocate abstraction points from the deep upper groundwater further downstream to lower surface flows. Leaving the deep aquifer intact as a massive natural sponge ensures delicate headwaters and village springs remain stable and flowing, even during severe drought. You can dig out all the silt you want, but those hyper-local fixes fall short without these regional shifts in how we manage the plumbing of the entire landscape. Right now, the survival of these rare streams relies on a highly fragile system. Decades of progress often hinge entirely on the sheer willpower of a few unpaid volunteers and local trustees. Because we've spent centuries altering the natural state of places like the Cleve for agriculture, they can no longer self-regulate. They require permanent, active human management to maintain their renaturalized state. In an engineered world, preserving these rare ecosystems requires active, permanent responsibility for reteaching heavily modified landscapes how to function as wild systems again.